Good afternoon all. Welcome to today's session. In this video, we will explore Ohm's law in depth, which is one of the most fundamental principles of electrical engineering. We'll begin with its theoretical foundation, then we will move into the mathematical formulation as explaining the real world examples like light bulb, and to conclude with the discussion on electron flow versus conventional current. So I do request you to stay with me until the end, and I'll pose a few application based on questions to test your understanding. So this is the content in this module I gotta cover. As part of this video, we'll begin with this Ohm's law, followed by Kirchhoff's law, and the basics of electrical circuits comes on. So we'll move with this Ohm's law. What does an Ohm's law states? It's like which establishes a direct relationship between voltage, current, and resistance, right? It's like it states that the voltage across a conductor is directly proportional to the current flowing through it, with the provided temperature is constant and the physical conditions of which remains same, right? Or the another word we can give the definition as at constant temperature, current flowing in a circuit is directly proportional to the potential difference between two ends of a conductor and inversely proportional to resistance R, right? But to the statement first, this would be the formula, I mean the mathematical representation of this Ohm's law, V equal to IR, and for the second statement what I have given is I proportional to V by R. So this is a simple linear equation forms that what would frame the basics of an electrical circuit analysis. Okay. When we say directly proportional, it implies that if we double that applied voltage across a resistor, the current will also double, assuming that the resistance is constant. Graphically, this is represented as a straight line when plotting voltage against current. However, it is important to note that the real resistor deviate from the ideal behavior under extreme operating conditions such as current density or elevated temperature. The linearity is lost, leading to non-ohmic behavior. I mean, non-linear characteristics, right? So now, resistance is the property of a material that opposes the flow of electric current, and its unit is ohm and defined as 1 volt per ampere. The formula is derived directly from the Ohm's law, R equal to V by I. So a resistor of 1 ohm allows 1 ampere of current when 1 voltage is applied across it. Conductance. It is the reciprocal of resistance. It is termed as G. The for mathematical representation is G equal to 1 by R. Its SI unit is Siemens, which is represented as capital S, which is replaced earlier informal unit called as mho, literally ohm spelled backwards. This concept becomes an extremely useful when analyzing parallel circuits where conductance values add more convenient than the resistances. Let's apply this concept to a practical case. Consider a 100-watt incandescent bulb connected to a 230-volt supply. The effective resistance can be calculated using R is V square by P. I mean, this derived from the formula P equal to VI, where the power current I is replaced in terms of voltage. Fine. Now let us extend our discussion to a resistivity rho, which is an intrinsic property of a material determining its resistance per unit length and cross-sectional area. The resistance of a conductor is given by R equal to rho L by A, where L is the length and A is the cross-sectional area. When comparing this, silver has the lowest resistivity and the copper has identical resistivity but more economical as per the industry standard. When we compare for glass or Teflon, the resistivity value is up to 1000 micro ohms. So it can be used for an excellent insulators. This is why engineers make material choice not only for conductivity but also cost, durability, and the ability. Why does the copper conduct so well? The atomic structure holds the answer. Each copper atom contributes a single valence electron, which is weak bound and easily liberated under an electric field. These free electrons form what we call the electron sea, allowing rapid charge transport. Thus, the conductivity at the microscopic level is tied directly to the atomic electron configuration. And this is the Ohm's law of electron flow circuit, where it can being flow in the closed loop. The copper wire is placed so that with the conductivity plays the major role here. The insulating ability was determined by the material we used. Okay, here we must clarify a common misconception that the actual direction of electron flow is from negative terminal to the positive of a source. However, for an analytical convenience, circuit theory traditional assumes conventional current flow, that the movement of positive charge from positive to negative. This historical choice does not affect the accuracy of circuit solution, but it is important to distinguish between physical electron flow and assumed conventional electron flow. Why does all this matter? Because when we analyze circuits, design electrical system or troubleshoot equipment, we are rely on Ohm's law to predict the current, voltage drops, and power consumptions. This law serves as basics for more advanced topics such as Kirchhoff's law, AC circuit analysis, and power factor correction, which we will cover in upcoming videos. To summarize today's session, it's like Ohm's law defines the linear relationship between voltage, current, and resistance. Resistance depends upon both material properties and the physical dimensions. Conductance is the reciprocal of resistance and is measured in Siemens. Real world examples like light bulb, filament have been illustrated, and the impact on temperature on resistance. While electron move from negative to positive, the conventional current assumes the opposite direction. So this is the fundamental principle of foundation of electrical engineering. If you found this session insightful, please like this video, subscribe to the channel, and comment your answers to the quiz puzzles I posted earlier. In next lecture, we will expand into Kirchhoff's law and learn how to solve the complex circuits. Thank you all.